My name's Gabriel. I'll go in more detail about myself later on in the presentation, but I'm going to talk about my experience in the motorsport world and how I transferred some of that knowledge into the America's Cup world. So just to give you a quick overview of how I've laid out the presentation, I'll start telling you more about me and my history. I'll tell you the history of the America's Cup. We'll talk about the 35th America's Cup, which is the campaign I partook in. The AC-50 was the actual name of the boat. I'll tell you a bit about the dynamics and the physics of the AC-50. We'll talk about the appendages, how they move, the powertrain system, and the steering system. So about me, I have a little family that was this Halloween, me and my wife and daughter. I have always been working on cars, anything with motors, engines. Grew up playing with RC cars, boats, planes and rockets. Built little race cars, Lemons cars. I went to Colorado State University for undergrad and grad school. I partook in Formula SAE throughout all of it. Huge, huge part of my life. I still partake in it as an advisor and judge from time to time at FSAE competitions. And then I interned at Woodward Governor as a manufacturing engineer, and this is my family again in Bermuda for the last America's Cup. While I was in grad school, I was recruited by Honda in their motorsport division. I was a performance engineer, primarily focusing on vehicle dynamics, did full vehicle and subsystem testing, wind tunnel testing, KNC, gearbox testing, all of it. I was the young guy, so that was the guy that they would send wherever it needed to go to test and get the data. I used this data to help correlate our simulation models, and then with these sim models, I would go to track events, primarily focused on IndyCar, and I would do DOEs, different experiments, helps with analyzing setups, finding optimal, aero settings, whatever the case may be. And the highlight of my Honda career was the 2014 Indy 500. A lot of the work, I did helped us win that, so really proud of that. While I was at Honda, I was contacted by a good friend to join the America's Cup campaign with Artemis Racing. I did join, and I was a mechanical systems engineer in the mechanical systems group. Primarily focused on the steering control system, but I also helped with the powertrain system and some of the wing control system. We're a small group, kind of did everything, but there was one small problem, and I didn't know anything about sailing. I had never sailed in my life. So I was pretty excited, but also nervous. So I did what I normally do when I try and learn something new. I picked up a book, and I started reading. That's actually a book I bought, and I read before I went to join the team. But anyway, this helped me learn the basics. And I'll give you a brief history of the America's Cup. It's got a rich history. It's very old. It started in 1851. This is actually the Cup from 1851. They still use it. It didn't have a name before that first race in the United Kingdom. And the yacht that won was actually the America, which is why it's named the America's Cup, not because it started in the United States. And ever since then, whoever wins the Cup, they are the defender, and they actually make all the rules for the following America's Cup Challenge. There's very few rules that date back to 1851, which is laid out in what they call the Deed of Gift. It's actually in the New York Supreme Court, but it's very few rules. The defender sets everything else, the size of the boat, where it's going to happen, nationality rules, any control restrictions, anything they want, and they can change it. Well, they have 1 year to make the rules, and then everyone agrees to those rules, and they all meet up and race. So that's kind of the history of the America's Cup, and this is what it is now, and what I partook in, actually. A lot more technology, speed, hydrofoils. When I did it, there was 6. Oh, sorry. Sorry, guys. There was 6 countries involved when I did it. This new campaign, there's only 4. but that could change at any time. So.
Is it because of money?
A little bit. This new campaign is mostly political, but I can kind of talk about that one later. A lot of people didn't like who won the cup, you could say, but I don't know. That's very, very wealthy people arguing over that kind of stuff, and I don't know the details. So I'll go into more details on the cup that I partook in, the 35th America's Cup, which just happened in 2017 in Bermuda. New Zealand won that cup. But just to give you a high-level overview of what the boats that I did, or I partook in, kind of hard to read, but there was some components. Sorry, let me back up a little bit. The previous cup was in San Francisco, and Oracle won again, and they decided to change it up a little bit. So they started to do some one design components, which was kind of sad, but there was still a lot of interesting areas to exploit. So the holes were one design, the shapes of the holes, the shape of the wing was a one design wing, but pretty much everything else was kind of free. But to give you a basic layout of the boat, it's a catamaran. They use a rigid sail. It's the same size of an Airbus A320, rough same dimensions as well. We have the rudders. Again, like I came from no sailing background, so I'll still give you kind of how I learned it. The rudders are used for steering, as well as with the little airfoils for stability in flight. The dagger foils, or the boards, are the primary lifting mechanism to get the boat out of the water. And then, of course, you've got the crossover beams that connect everything, a trampoline so that you can walk and run across it. But I'll go into more detail on some of the areas.
The hydrofoils, those are not one design?
No, those were free. Yep, yeah. Okay. They just gave a boxed area and free to do what you want. I'll talk a little bit more about them later as well.
There's only one wing regardless of wind conditions?
Yes. Yeah, yeah. The control systems in the wings were open, so we did build multiple wings with different control systems for various conditions or various types of tests we wanted to try, but the spar and the shape of the wing was the one design. So it was Oracle's way to try and cut costs and get more teams involved. But I think it's similar in Formula One. You start cutting costs, you just spend the money elsewhere. So doesn't really have the effect, in my opinion. So, but to go on with like the foils and how I related them, this is equivalent to the tires. You have 4 contact patches, they had 4 foils. This was used to get the boat out of the water, to reduce drag, to increase speed. The one in front was a dagger foil. It's like a, I'm not sure if I'll say it right, the Sith, like a Grim Reaper has. The same shape, it's an L. As I said, it's primary lifting. And then the rudders, they do have airfoils on the bottom. This is for stability in flight, and pretty much that's all it's used for. The wing, going a little bit into that. It is a rigid wing. It allows us to achieve 3 to 4 times what the speed of the wind is. It's pretty impressive. Really, really incredible feat, in my opinion, of the America's Cup campaign. A little bit highlights, it's exactly like an airfoil of an airplane. You've got some ribs and a trailing edge, a leading edge, and shear webs and control mechanisms in there. And then the crew. I equate it to the power steering or any auxiliary pump in an engine. Oh, sorry, I forgot to say the wing is like the engine of the boat. The crew is really all the auxiliary pumps. And this might sound kind of crude and cruel, but they are humans, but they're treated as an actual component of the boat. We analyze everything about them. There's a whole sports science group on every team, exercise physiologists, doctors, nutritionists, chef. They control everything about these men, the food, their workout routines, everything is controlled.
There's no women on the team at all?
On the engineering and design team, we had women, but not in the crew. Yeah, and it usually comes down to strength, as the lady was mentioning. We have, I'll talk about it more later, but this is a dyno that most teams develop their own dyno, so this was a hand crank dyno, so we knew all of their power output, and we continually optimized their power output. But it was a very serious part of the boat, not just human. Like, we treated them as an equipment. So. That might sound bad because I loved all the sailors. They were really great guys. Nothing against them. So we'll go a little bit into the dynamics and the physics of the boat now that we kind of got the basics. So this is how the foiling cats work. It seems kind of simple, but you've got the primary propellant force is obviously the wind and the force generated from the wing. This is wanting to basically capsize the boat, overturn the boat. So to resist that overturning moment, the primary factor is this dagger board. This is what's putting most of the lift to resist this overturning moment. It's kind of hard to see, but the two rudders in the rear also move fore and aft, and they're split. They're doing opposite angles. The one that's on the leeward side, and leeward is a term for away from the wind, the one that's on the leeward side is actually providing lift to help the dagger board resist the wing. And the rudder on the windward side, which is with the wind, is sucking down to pull against this overturning moment. And this is also why we have our movable mast, which is the crew, on the windward side to help resist that overturning moment again.
So nothing from the dagger boards. The dagger boards don't resist the heel.
They're pushing up to resist the overturning moment. They're not pulling down. So in a traditional boat,
But the dagger boards are pushing up, but the rudders actually
stabilize.
One side pushes down, one side pushes up.
Yeah. So the side that the crew's on is sucking down, and then the side that's with the dagger board is pushing up to help the dagger board. And then more on the dagger boards in detail. So kind of what was asked earlier, this was the huge area of development in this campaign because it was just a volume and have fun, do whatever you want in it. But they did limit it to 4. So we were only allowed 4 specific dagger boards for the race. We could only develop 6 for testing. So it was a very stressful time trying to figure out which 6 to finalize and then ultimately pick the 4. And they're all different shapes, sizes. You have S-curves. And they were developed for specific wind ranges. The Cup was allowed to be raced, I think, from 6 to 20 knots of wind. And so they were all designed in specific wind ranges. I have an example of 8 to 12, 12 to 15, but just small wind ranges to get the boat up. And it's always a compromise between lift and drag, just like in car aerodynamics. And you can kind of see the really long boards here. These are for low wind. It's to get the boat out of the water as quick as possible. Whoever can get up is going to win. And then these really short, stubby boards here are the high wind boards, because I'll discuss it on the next slide, but there is a limit to the height that you can have. So there's 2 concerns with foil design. Now, I didn't do detailed foil design, but everyone on the team knew this kind of stuff. It's ventilation, which is when the foil gets too close to the surface of the water, you can get a mixture of air and water, which affects the pressure on the foil, and then you can end up falling or losing the lift force. But the biggest concern with foil design is cavitation, and it's actually boiling of the water from pressure drop. And this occurs when you've gone beyond the speed of the design of the foil. So that's why it's so crucial, balancing between these 2. If you have too much lift, you'll get to ventilation. But if you also go too fast, you'll get to cavitation. And then you end up crashing, or in really severe circumstances, you can have capsizing and what happened in New Zealand here, pitch poling. I mean, that's a combination of many things, but once you get too close to the surface and you have this ventilation, you lose control of the boat. You lose control of that foil. And as I said earlier, the wing was probably the most impressive thing to me, even though the dagger boards were really cool. This is a solid wing, and it's all composite, so all carbon, but it's designed in a way that it can twist. You can kind of see it here. And it has a very severe twist. And this is because as you go up in altitude, the wind speed changes. And it's enough to dictate that massive twist on the wing. And even though, like someone said before, the America's Cup is Formula One on the water, I truly believe that in the technology. They still use some very low-tech devices to help them in sailing. And that's these telltales or airflow telltales. They're just tufts, yeah, little pieces of fabric. And that'll help the sailors know when they've reached a stall point on the wing and when to adjust the twist or the camber or the angle of the wing. So now we've kind of gone over the basics. I'll go into the appendage movement because I primarily focused on this area, controlling the appendages. So back to the car world. Most people know what caster is, the angle fore and aft from a side view of the front. It's the same in the America's Cup. It's called Rake. This actually changes the angle of attack of the foils in the water. So this is how you control flight. In the rudders, it's for stability. But I'll try and always equate it back to caster, but I'm sure I'll say Rake quite a few times as we go on through the presentation, and that's this angle. Now tow, that's the in and out angle from the top view of the car. It's the exact same in America's Cup. Thankfully, nothing different. And it's used primarily for the same reasons. Camber, from the forward angle, or the angle in and out of the wheel from front view. In America's Cup, it's called Cant, or in sailing, excuse me, it's called Cant. And this is a mouthful, but only the Dagger Boards can cant. But they're the only appendage that's allowed to cant on the boat. And this is used for riding moment. As I discussed, some of the boards have a S-curve. The reason they have that S-curve is, in addition to canting the board, you can get that force that the Dagger Board is providing further out to resist the moment of the wing that's wanting to overturn the boat.
Is that like a ratchet type of system? Or ratcheted this way or this way? I mean,
No, it's, I have some details later, but it's all hydraulic system. So there's a hydraulic ram. Every team had different, the control systems were free.
and who controls that?
The sailors. So that,
I mean, the guys on the far side?
yeah. So each team had different strategy in how they laid out the sailors, but our team, the helmsman, so the guy that's steering the boat, the one I worked a lot with, he's controlling everything on there. And then the guy in front, so you see this is the helmsman here, and the guy in front was controlling the wing, handling the twist and the angle of the wing. But other teams, they split it up differently. New Zealand, one of the ingenious things with them is all the sailors that were grinding and doing different things, they all had different responsibilities. And the helmsman just steered the boat. So now we'll go into powertrain. This is more really interesting stuff to me as well. So in the automotive world, this is a powertrain. You've got the engine, the gearbox, the diff, the axles all going out to the wheels. You know, that's what everyone thinks of as a powertrain. In the America's Cup, this is our powertrain. So these guys are really, really impressive. The most amazing athletes. Most of them are ex-Olympians or current Olympians, but they're able to generate 500 to 600 watts sustained, and these races are 20 to 30 minutes. They can do bursts of 1,600 watts, and that's in about 2 horsepower, and they're paired up on each pedestal, so we have 8 horsepower in this boat, if you want to think of it that way.
What sport do they typically come from?
Well, so after the last campaign, people started to learn we need upper body strength, crucially. So Chris Brittle he's actually a sailor, but also power lifted, this guy. We had 2 Olympic kayakers. The Americans had rugby players, football players. It was primarily heavy upper body strength type sports. So kayakers were really popular. So.
What is this power used for? Is he generating electricity or what?
No, so they're actually, they're powering the pump, and it's filling the hydraulic reservoir. So or pressurizing the reservoir. And then from this reservoir, you control all of the appendages with the hydraulic rams. And the reason we do this is because the forces and the loads are so high on these appendages and the wing, because the boats are so fast now, that it's possible, but it would be a lot of mechanical advantages with pulleys everywhere and all these systems. So it's much easier to do it with hydraulic system. Yes. Well, they still call them grinders. The guys that are doing this are called grinders. So that's another, comment on them. And there's one more thing I wanted to add, is that in a typical day, they do 2 races and they burn about 8,000 to 9,000 calories. So it's really extreme.
Do they keep this thing going constantly by, running in shifts? One guy runs it for a while and they bring in somebody else, or is it just
Well, it's 20 minutes.
pressurize it and it goes into a reservoir?
It goes into a reservoir, and I'll touch on it a little later, but that's a big challenge of this last America's Cup is we didn't have enough power. So, but I'll go into it more later.
And, yeah, the New Zealand team used a bicycle
Yeah.
rig, which nobody else had thought of, I guess. or-
Yeah, and I'll touch on that one later too. That's really quite exciting. So I kind of hit this already, but yeah, basically they're powering the pump, and they're filling up the reservoir with pressure, which is then used to move all the appendages and all the control systems. Kind of going back again to the powertrain comparison, this is what we think of as cars. You have an engine on an engine dyno. With that, you get, it's really hard to see, sorry, power characteristics of the engine, dyno curves. That, in motorsports, with track layout, conditions, and other variables, you get an optimal gearing. You decide on the gearing for the track. It's the exact same thing in the America's Cup. So we had...
Would it be against the rules to have an animal on board supplying muscle power?
Yeah, that is one thing. It still had to be human powered, so I think that's how they got rid of that. Yeah. But with the grinding dyno, we get the power characteristic of each human. We use this to pair the two together, and then with the flow rates or any other variables that we have, there's many of them, you get the optimal gearing again. So pretty much the same process.
Does each grinder station have its own pump?
Some teams, yes, some no. So it just depended on the team. And it was really hard to see because they're all hidden. So you could get a large enough pump and then connect it all together mechanically and have the 2 grinders, the 2 pedestals running together on the same pump on a clutch system. It's more complex, but you could do it. Or you could do smaller pumps on each pedestal and then optimize the gearing for the pair of grinders.
What did you do?
I actually, at the end, I think we changed it to 2 pumps, but I didn't honestly get involved in the powertrain system too much. So the way they used, what I did in the powertrain world was we had a couple different ideas, and with America's Cups, there's not, even though I say there's not enough time, but the rules are so open, you're almost just throwing spaghetti on the wall and seeing what sticks, and then you figure out and optimize. So one of the systems I developed or helped develop ultimately wasn't chosen. So my powertrain system didn't get in the boat, but that was for multiple reasons. And so they had 2 or 3 teams developing it on the side in parallel, and whichever one was most efficient, most optimal, they went with. So it's fair enough, no hard feelings. The one thing that, I mean, I was primarily in charge of the steering system, so we'll talk on that one as well. This is kind of on what you were saying with the cycling. So the America's Cup, it's truly pretty impressive with technology, and almost all of it's pretty hidden, just like in Formula One, that you can't see a lot of it. But I kind of also touched on it before. With the rules changes, Oracle decided to restrict the number of sailors down from 11 to 6. So they effectively halved the amount of power that we had on the boat. However, they also added rake control, which was the caster control. Previous Cup in San Francisco, you couldn't dynamically adjust it. So it was actually on a pin, and you picked an angle and pinned it. But it ended up, even though the racing was really exciting, the boats didn't foil very steadily. They were always crashing down. So they knew that they would add rate control with this, but then they cut our power in half. So we had more power demand and half the power. So every team was faced with the exact same problem and what we were going to do with it, which is why we had so many groups trying different powertrain options. As a team, we decided to focus on efficiency and weight, so reducing friction as much as possible, reducing complexity, and then getting the weight down. We did it. We were totally fine on the race course. But as was mentioned before, the New Zealand came out with the cycling because you have more power in your legs and more stamina, and kind of what you were asking about where the athletes come from. So New Zealand had Olympic cyclists on their team, but they kept it very secret. However, it wasn't really a surprise because everyone, including when I joined Artemis, we investigated this and we built a whole rig and tested it. But there's a few reasons why we didn't go with it. Some political, but others safety. Like you can see right here, when they're running across, you have to jump in, sit down, and clip in. And then if you crash or capsize and you're clipped in, it's very difficult to get out. And that was really important for Artemis because my team, the sailor, actually died in San Francisco, drowned. So safety was critical. And when we couldn't figure out a solution to that, they basically canned the idea. But yeah, it was really impressive that they achieved it. And as I described too, because every sailor was just pedaling with their legs, they had each sailor controlling something different so that they could separate and compartmentalize their responsibilities. So you wouldn't have the helmsman doing everything, trying to figure out everything. So all he had to do was steer and think about tactics. So now we'll go into some more details on the steering system that I developed. This is just kind of my methodology. I like systems engineering a lot. I think in the systems engineering way. I tend to do a V model in most of my projects. I do figure out high-level system concepts, which end up, or high-level system targets, which help set subsystem targets, which help set component targets. And then you design those components, validate them, go up the V, validate them in testing, validate the subsystem, and then validate the full system. This is a lot of words, but basically working with the team came up with all the requirements. And another thing that helped set full system requirements was simulation and sensitivities. So I used to do sensitivities a lot in the motorsport world at Honda. And these sorts of things you can do with simulation models, and it tells you like how much time at a track can you get per weight or per pound, what's the sensitivity of aero. So with these sorts of things, you can kind of understand what areas you need to focus on. And it was very similar in the America's Cup world. The only difference, it's also hard to see, I'm sorry, you ended up having to do a double derivative because you have two things you're looking at. You have the power of the wind plus the weight and boat speed. So it's multiple things to consider. So it's really hard to see, but for this sensitivity plot here, it's weight. On the left side, it's the sensitivity of boat speed and mass, and on the bottom, it's total wind speed from 8 to 20 knots. And what was interesting, which as every team started honing in on this, is as you get up in boat speed, the sensitivity to weight goes down and down and down, and eventually it flips sign. So at 14 knots, it actually goes the opposite way, where it's beneficial to have weight on the boat. So now it was a big compromise of what do we do? Because the America's Cup rules, they'll let us sail anywhere from 6 to 20 knots. But right in the middle of that threshold, these boats are very sensitive to weight. But this is when you start looking at a lot of other things. Historical weather data. Bermuda was always 8 to 16 knots. So as
18 knots is what, like 30?
yeah, 20-ish or a little under 20 miles an hour.
Oh,
So.
okay.
But so as a team, we primarily focused on the lower wind speeds and built the boards and developed everything around the lower wind speeds because that's what Bermuda was at that time of year. So kind of going on, once we have the high-level targets and I know what I need, I build a skeleton model. And this is CATIA, but any CAD package. And this is points, lines, and planes, just the known components. And I try and build them all on variables and parameters. and everything is built off of those parameters, so I can adjust those parameters as needed. These points come from other groups, like the structures group, the aero group, but they have a range, and I can move them within that package. But using this and with the parameters, I can do things like I wrote a separate script and interfaced with CATIA and an API and moved all of these points around and then ran them through the range of motions and got all the data out of it, basically doing a massive DOE on all the points and understanding an optimal solution or a few optimal solutions. Some of the example data that comes out is stuff like this. This was just really simple, but using this plus even more analysis that was done on those points and those DOEs that I moved the points around, I could fixate on an optimal solution based on kinematics. Once that's done, we go down into component design, design everything detailed in CAD, a lot of FEA, hand calcs for all of it. We ran really low safety factors, about 1.2-ish. So it was really crucial to not fully trust the sim packages all the time, but I'm a kind of a skeptical person in that world anyways. I prefer hand calcs. But you still have to use it to help guide you. And then validate it was crucial. But with the low safety factor, you'll see a failure here on the Japanese team. And that was actually a control system failure, so it's my equivalent, but in Japan. So that's why it's really crucial to make sure you have the parts at the limit, but you don't want to carry extra weight. And from there, you start building up the subassemblies, testing those subassemblies, checking for clearances. This is the tiller, angle sensors, upper bearing, the whole assembly in the boat. And this is a unique thing I wanted to highlight a little bit. I talked before about the Rake, which is like the caster, changing the angle of attack on the wings. They're constantly adjusting it. And because it had just been introduced to have rake control in this campaign, most teams were sticking buttons and switches on the steering wheel like we did. But as a helmsman, you've got so many other things and screens that you're looking at and the race. It's hard to remember where those buttons are in every single one, so they're constantly looking down, trying to adjust. But me with some of the Sparkies in the group, we took some of the motorsport knowledge, and this is an actual paddle switch lever from Racing World to change gears, and incorporated that on a pedestal above, right in front of his fingers, so he didn't have to take his eyes off of the screens or the water anymore. He could just move the rake and change the boat, the attitude of the boat with this. And then finally you do the full system. This is most of the steering controls, at least, the buttons and the hand rake control there. But you build it up, and then you go do full system testing, data analysis, validation, and then optimize the system again. And you continually do it until the race, because there's no real restriction on it. As a team, we built 2 test boats, and then we did the final race boat. Okay, there's one last thing. I wasn't sure on time, but I think we're okay. So there's one last thing I wanted to talk about, which was pretty unique, I thought. As I discussed before, this was the first campaign that they allowed rake control. And since I was in charge of the steering system, I started, and I ran through that script of moving all the points and getting all the resultant data out of it. I discovered a phenomena akin to bump steer, rake steer. And in bump steer, when the suspension compresses, the tire will toe in or out. It's usually introduced in passenger cars for safety reasons, but in the motorsports world, it's really bad. So you do everything to minimize bump steer, and you really have none in motorsports. But in America's Cup, I discovered we were having quite a lot of bump steer or rake steer. And this was changing the angle of the foils and towing them in and out, which was actually introducing more drag on the boat, which could reduce the boat speed enough to cause it to go below the liftoff speed, and then you end up crashing down, and that's the end of the race. And the primary, a big reason that this came into effect was because in the San Francisco campaign, they were able to foil 50% of the race course, and they were able to do foiling jibes. But with allowing dynamic rate control, every team discovered now's the ability to foil 100% on the race course, and you could do a foiling tack. But the first team that touches down, or if you touch the water, it's over. You're done. Your boat speed is halved immediately. And this was a promo video done by Oracle, but it talks about the foiling tack. Sorry.
Today we went out there with the goal of doing a foiling tack, which we've never done before in these boats.
Full foiling tack. See this one?
We had some catastrophic fails in our attempts and some big crashes in attempting to do it, but we eventually did it.
So that's the holy grail of this last campaign. Ultimately, every team did it, including us, but that rake steer issue had to be addressed in order to keep the boat up and foiling. Similar to the car world, it's primarily geometry. It was kinematics. As you can see here, these crossover connection tubes, if they're pretty far away from the rudders and the tiller, you end up with a really drastic change in tow. This is just like a bump steer graph. As the foils rake, you end up with a drastic change in tow. And this was France's solution. This is Team France, but they moved these steering crossover tubes very far out, pretty close to in line with where the rudders are, and you end up with very minimal to no tow effect at all. But
So the rudder interconnect is mechanical.
yes, yeah,
The rake is hydraulic.
yes, sir. And then there was a lot to it as well, but the rudders were limited per the rules to plus or minus 1.5 degrees, 3 degrees total rake. But I was talking with someone about the rule book is like 17 pages long, so it's pretty open. So they didn't say where you started. So we had actually a long, pretty trick way of adjusting the 0 point of the rake, and then you just had 3 degrees total from that 0 point. So, yeah.
Looks like when you're on tack, you're on one foil, you do your tack, you actually put the other foil down for a time period. How much trouble was when you actually had to go shift from that one foil to two foils and back in terms of keeping that stable?
That's actually was the largest challenge for the hydraulics group. They were the hydraulic controls group. Was you could semi-automate systems in that they allowed you to push one button and move everything. So as you go into a maneuver, they just push one button and then it controls decanting, raising, and lowering the other dagger board all seamlessly. So that's where the controls guys really came in, the software guys really came in. But it was extremely difficult to get right. A lot of testing. And once you get it right for one board, it was totally different for one of the other. Yeah. So it was really, really difficult to get that right.
Uploaded almost a new software package for every race, depending on wind speed and
Yeah.
whatever.
Yeah. And then I don't know if this was. Anyways, that was the end. But yeah, it's really difficult to change the boards as well. It's a long process. So even though there's 2 races every day, you kind of stick with the boards you put in the morning. So you don't have to adjust software too much, but you did have to figure out all of those software problems before you come to the race day.
So there's no racing by the seat of your pants?
Not really. Yeah, you'll be in quite a bit of trouble.
How much,
It's like
Sorry. Yeah.
Rubber end up actually out on the water in the boat?
Not in the cup boat, unfortunately, or fortunately, but Artemis took it very seriously with losing one of our sailors. I mean, actually some of the colors and everything was attributed to him. Bart Simpson was his name. And so nobody was allowed on the boats unless they were a sailor. But we had chase boats, 3 chase boats, 1 engineering boat. The other 2 boats were rescue divers. And then I went on the engineering boat a couple of times, yeah, and it, had waterproof laptop screens, so we were analyzing all the data as we were sailing. So.
How much force did the Dagger Boards have to counteract to keep the boat upright?
Oh, I don't remember the number off my head. Not even the range, sorry. Sure.
I don't know that much about sailing, but so you're inserting and taking out Dagger boards
Yeah.
manually,
Uh,
or is that automated push button?
Semi-automated, yeah, push button.
Where were they stored? I mean, how do you change them?
To physically take them out?
Change from one type to another.
Oh, well, that's a huge, long process. I don't think I have a picture of. I would have to scroll back.
You could change it right in the middle of a race?
No, no, no.
Oh,
No, sorry. Yeah, it was. Sorry, might have to like scroll through a whole bunch, but they only put 1 board in the water at a time, and then once they change direction, they'll put the other board in, and that's primarily kind of due way back to the physics graph I was showing. You can see the 1 board there, but it's very difficult to design a board, an airfoil, to do both directions of lift, because in this case, you would need on the windward side, where the wind's coming from, you would need it to be sucking down, not pushing up. Otherwise, it would be adding to the wing and wanting to flip the boat over. So both foils are designed for constant lift. And that's why you only put 1 in the water at a time. But going through a maneuver, there is a crossover point. And especially with the foiling tacks and foiling jibes, it's very difficult to get that right.
So what was the postmortem on your success or not success?
Okay. So America's Cup is a unique career in that everyone's on contract. And in the contract, it states if you win, you get retained, and they give you your salary, and you get a year off and all benefits. And if you lose, your contract's over. So we placed 3rd.
How about the racing success of the boat? What was the postmortem on why you didn't do better?
Actually, so the way America's Cup works is the defender doesn't have to race until the very end. So you have all the challengers, they go together and they race each other. And they say, and I do believe, one of the greatest matches in history of the America's Cup was Artemis and New Zealand for the Challenger Series. So we beat all the other boats except New Zealand, and New Zealand went on and won. They went on and raced America. However, there was a round-robin series in the beginning. This was also kind of nasty political, but America wrote it in the rules that they were allowed to partake in that round-robin, even though they couldn't get knocked out because they were the defender. A lot of teams got upset, including ourselves, because that allowed them to see our tactics, everything, and race against us before defending for the cup. Yeah, but we actually clean sweep them as well. So there was an argument as to who had the faster boat, us or New Zealand, because New Zealand swept them as well. And it was extremely close between us and New Zealand.
Since these have gone so far high tech, is there anything that translates to a normal sailboat?
Riding moment is riding moment.
Yeah.
You always have riding moment. You always have wind blowing over a surface. So it's.
I mean, I know that like the hydrofoil technology, it's a lot of ex-America's Cup engineers have gone on and started other foiling companies. Like it's gone into kiteboarding now, surfing, and it's all because of this world. And you know, we worked a lot with suppliers like sailing suppliers for the hydraulic pumps and those sorts of. They were really interested in advancing their technology and putting that back into the systems that they provided for customers. So
The tech transfer is not really into conventional sailboats and in some instances
yeah,
into other water sports.
yeah.
Well, I saw foils on a boat in a marina not too long ago. So they are
Yeah.
I'm wondering, what is the rule, if any, on electric power on board? Can you bring a big battery, or what do you do?
No, that was, so they limited, I can't remember exactly how they restricted that, but I think they had one battery that we were allowed to use, and they supplied it. But that's just for sensors.
Yeah. It's just, is it like a car battery?
Yeah, yeah, or a marine battery, but yeah, typical 12-volt battery. And I think they just limited the total voltage. Maybe they didn't give us a specific battery. But yeah, kind of on that note too, as I was talking with the grinders, I mean, they're done after a race. It's just such a gruesome, excruciating thing for them to do. So on the first 2 test boats, we actually had a system that I helped with as well to plug in an electric motor. So they didn't have to actually be on the boat. So we could do all our engineering testing, because if we had them, we would only get maybe an hour. But with the electric motor, we could go out and sail for 6-8 hours and actually do real testing.
Yeah. Is weight a consideration with regard to that? I mean, that you have an electric motor, you keep that on board all the time and just not
Yeah.
use it?
Yeah, on one of the test boats, yes. On the other, we were able to take it off. But yeah, it was a big consideration, and we tried our best to balance the weight. Another thing I forgot to mention, America restricted the size, Oracle restricted the size of the test boats, so they were much smaller. They were actually 45, well, not much smaller, they were 45-foot boats. But so it was always a game of trying to correlate that to what the 50-foot boat would be. Originally, it was going to be a 62 or 65-foot boat, but then they shortened it even more.
I was just thinking of the possibility, maybe it's impractical, to have a small windmill
Oh, yeah.
generate electricity rather than,
Yeah. I don't know.
You are moving forward, but
Yeah.
of course, it takes a certain amount of drag to run the windmill.
True, yeah.
Where's the next race?
So New Zealand one, it's in New Zealand. They're doing it in New Zealand. And they, like I said, everyone makes the rules. So they made it a monohull. It's foiling. They got rid of the rigid wing. They actually banned cyclers. So now you can only use hand grinders. Yeah. So,
Hamsters and
yeah.
That's what I say.
Yeah.
What's the minimum weight, and is everything basically carbon fiber?
Majority. Anything that's metal was titanium, pretty much. So pretty much everything was carbon.
And the minimum weight for the hull?
Oh, I don't remember the minimum weight off the top of my head. I'm sorry. There was a minimum weight they didn't have a weight on the boat, but they had a weight on certain components, such as the sailors, because they were a huge weight or load to help resist the moment on the wing. So most teams actually weighted up their lighter sailors to get that weight, but then it was a hindrance for them running back and forth. So.
Bulking up?
Yeah.
Is what they call it.
Yeah, I know. Yeah.
After the race was over, what technical changes would you have made in retrospect?
Well, that's a good question. I think more time on the grinding and the powertrain system, because we had to make some compromises on other systems, like the wing control, which was kind of sad. In the steering world, I was pretty proud with everything I did. A lot of the guys were happy with it. There was really no complaints and changes. I showed you that lever for rake control here. On the boat that ultimately got the final race boat, they got removed because someone else had a really ingenious idea. It was Oracle, actually. But they developed a twist grip on the steering wheel. So they had 4 twist grips to adjust rake. So we copied it, but yeah.
Are you going to be on another team?
No, I was contacted by one, but with my small family now, I kind of would rather not. It was really, really exciting, and I loved it, and maybe I'll consider it again in the future, but it's pretty brutal. There's no time off. You work 6 days a week, mandatory hours, and you just, no questions asked. You have to be there, even if you're got nothing to do and you're surfing Facebook. They don't care. You just have to be there.
Where did you spend most of your time, in Bermuda?
No, we were based in Alameda. I actually still live in the Bay Area, but we were based in Alameda, just outside of Oakland, and that's where most of the team was. And then we just moved at the very end to do Bermuda. Only a few teams moved to Bermuda. We explored it, but there's not much industry there. So we were trying to do a partnership with suppliers in North Carolina to ship things over, but it was just too much. And Bermuda is extremely expensive. Even though I complain about San Francisco, that's on another level. So, yeah.
What's the limitation on automation? Are there certain things that have to be done manually no matter what?
Yeah, so they have like the spirit of the rules. They say, you know, it should be in the spirit of sailing and human powered. But there was kind of an open area that we were exploring when I first started the team. They didn't restrict closed loop control, and they didn't restrict automation. So we actually had quite a few systems set up to do full closed loop control, and it was really, really cool. But then they updated the rules and added those lines. Another thing that's kind of cool, the Defender makes the rules for a certain period of time, usually about a year. And then the original challenger, it's usually just one team, will agree with the rules on the Defender, and then it's set in stone. And the only way to make a change down the road is all the teams have to agree to change something on the rules. And so by the teams, that's the owners, so like the billionaires. And they all sat down, and someone brought up that there was a loophole in the rules of this automation and closed loop control, so they all amended the rules and changed it. But yeah, there's not much as far that was allowed.
Do you expect Oracle to compete again?
No, they're actually not. I was kind of talking with someone earlier about it, but politics again. Larry Ellison wasn't too happy that New Zealand won, so he's actually created his own racing series. He just announced it, but it's these boats basically. It's a spec racing, so everyone has the same boat, and so.
And that's going to be when?
I don't remember when he's announcing his, or when they're starting to sail.
Not direct competition time-wise with the America's Cup, right?
No, but close.
Okay.
What's the estimated budget for a team?
They tried to keep it under 100 million, but it was far north of that. So that's also actually a unique question on, like, Larry and Oracle in the previous campaigns. They had no limit, and no one really knows what they spent. It's pretty astronomical. But for this last campaign, I heard rumors. Everyone in the Cup world heard rumors that he kind of got, maybe not bored, but he wanted to challenge his guys some more, so he gave them a budget cap of like 150 million or whatever it was. And he said, you only have this much. I'm not just going to give you an open checkbook. And you could say that's why they lost. I don't know, but it was.
How big was the overall engineering team on yours, please?
Ours, I think we had 17, 18 people. We had a few remote in South America and Europe. But yeah, pretty small team. Mechanical systems group, we had 4. One of them was an intern, but yeah, it was a good group of guys. Then you had structures and aero and dynamics group and the hydro group. So.
Regarding pedal clip-in,
Yeah.
what's the safety concern there? Because mountain bike riders clip in and out all the time. It must be they get knocked unconscious and they're capsized?
Yeah, I mean, I completely agree. I was totally for the cycling. Most of us were. There was a lot of other higher up arguments against it, and yeah, we argued exactly what you said, that, you know, it's used in pretty extreme conditions in mountain biking, and the counter to that was exactly what you commented as well, is the fear of if you get knocked out and you're still clipped in, because the sad fact of how the sailor passed away in drowning. Similar aspect. They think he was knocked out, and the boat disintegrated and tangled itself up, so he couldn't get out. And even the rescue divers couldn't get in. So they did a lot of changes as a whole cup, everybody. All the sailors now have small air tanks and knives and rescue equipment. And every team, I mean, our rescue divers, I don't have pictures of them, but they were all ex-Navy SEALs, Rangers, like really, really extreme guys. And every team made sure to include multiple, special forces people.
So those sailors have air?
Yeah, just small one, enough for like 5 minutes. So, yeah, they all did. And then they all had knives.
So the hydraulic reservoir would store some energy?
Yes.
Okay, so were they grinding all the time to keep it pumped up?
Pretty much.
Pretty much like all the time.
Pretty much, yeah. Actually, this is a good one. You can see in the cycling, they had so much power that there's quite a few moments where they don't cycle. And sometimes we have the grinders directly connect to a hydraulic ram to actually power it instead of the reservoir. That's when you need the really huge burst of energy. But most of the time, it's just a constant, nonstop, just keeping it going. And they had displays on the pedestals. I think you maybe mentioned the hamster wheel or something. We had a famous sailor, forgive me because I didn't really know he was that famous, but Loic Perron, he's I guess world famous, sailed around the world multiple times, broke all these records. When he goes to Europe, he's trampled like all these Hollywood movie stars here. But he was one of our advisors, and he used to call them hamsters, which is why it didn't really matter if you knew how to sail as a grinder, you just needed the strength. And so we tried our best to make it idiot-proof. They had screens. You can see them all looking straight down. There was a screen there, and it was just telling them, this is your target, hit this cadence, hit this power, and go. And then lights for when to change gear. And
But there was a control to go direct to a ram?
Yep. And they all communicated with each other. I think ultimately we had the helmsman or one of the tacticians would tell them, I'm going to change you to direct drive. And they could every team had different things that they directly drove. Most of the time, in our case, it was like to lower the foil or move the wing, like in a quick instant when you needed it. And that's where the flow rate came into consideration. So you would change gear into a certain gear to get that flow rate that you desired. But it was also hard because as the race went on, their output decreased. It's just stamina.
The grinders could see a column, but the bikers, how would they know when to stop and start, so to speak? They also had screens. There was a lot of in motorsports, everyone spies, and we all had spy photographers. Every team had them as well. And yeah, you could see inside and some other pictures that they had their own screens to tell them when to do things and what to do. I also really loved how one of the arguments we were told was the aerodynamic considerations of standing on a bike. But, just look at Tour de France, anything, and look at what New Zealand did. They actually staggered their sailors, their cyclers, in height to get this nice aerodynamic foil shape when they're all hunched over, like the tallest one, and you get a nice foil. But, yeah.
What was the highest speed you guys ever hit out on the water?
Just past 50 knots, so, yeah.
So when you tack or jibe, you're going to have to change the rake
Yeah.
of the rudders. Okay, that's a control the helmsman had to make while tacking, as well as steering.
No, it was automated in a sense that you could push the button and it would just change it immediately. But he had to know when to initiate the maneuver.
But it would have to be controlled because, right,
Yes, yes,
It was not just pushing a button, but actually adjusting,
yes,
constantly adjusting.
yes, yes. So those were on knobs or other sorts of things. But the paddle switch was for straight steady flight.
Does everybody have earpieces and microphones?
Yeah, yeah, they all do. And it's still really hard to hear. We had some really, really,
And they're wearing helmets, right?
yeah, yeah. We had some really unique ones, like what the, I guess, Special Forces guys use. And like you don't even have to speak and you can hear it, but it never really worked for us. So we have these old school, just like these guys, old school headsets, and you know, that's what worked. Yeah.
Not broke, don't fix it.
Yeah. But the kind of what Dean was asking about the speed, one of the most interesting things I learned is that the boat could sail with no wind, and just changing the angles of the foils and the dagger boards, if you had them all out, it could sail upstream against a current of 4 to 5 knots. It could actually sail against the current with no wind. So.
Are dagger boards affixed down below, or how you say you have to store them?
You mean like they go up? You can see it going up here.
Yeah.
This is one, and this one's just deployed, so it's down. And so,
It's shot there or it's sticking up.
yeah, like this one's going down.
It does come up. Okay,
Yeah, it goes up and down. Yeah,
Like a periscope.
yeah, and this one's up. And
Does it have rack teeth on them or something?
I'm sorry?
They have like a rack tooth on them to lower them and raise them?
No, actually, it's on. It was a lot of effort into the friction characteristics of the bearings on those, so they were just free. There's a lot of development in the up-down system. There's pulleys and then a hydraulic ram pulling the pulley. You can't see it in here either, but yeah, they were free. If you just let them go, they would.
They drop.
Yeah. But then, you know, there's so much more to consider, because if the force that you hit the water with can really disturb things, and the angle that you hit the water. So a lot of effort went into controlling that drop speed. Still wanted to be as fast as possible, but when you approach the water, you needed to control the angle. Yeah, but anyway.
See, okay, I saw it.
Yeah. I don't know, any other questions?
So when they first hit the water, are they generating lift, and you have to push against
Yeah,
the lift
yeah,
to get them down?
yeah.
You said there was a pulley, or is that just a pinch roller moving it up and down? Dagger board.
No, there was multiple ways that teams did it. Some of them actually had ropes inside of the boards, and then a pulley system throughout to pull it up and down. Other teams had, I would have to go way back, but the image that I had of the dagger board, they'll have a fixture on the top, and then that would be attached to a pulley system. There was a lot of effort into the whole up-down system and how to optimize it and how to try and take mechanical advantages to try and reduce hydraulic need. Because if you have varying forces, that hydraulic ram's constantly pulling energy to try and keep it steady. So we looked inspiration in airplanes, like their landing gears have a locking mechanism. So a lot of teams went with locking mechanisms like we did to lock it down. And then you just don't need any pressure to keep it at the level it is.
Could you control camber?
Yeah, yeah. Only on the dagger board, on the board.
But while you were sailing, you could change the camber?
Yeah.
Was there Rake on, if there's Rake, so Cant,
Yeah.
call it Cant. It was
Cant.
And you were controlling Cant on the rudders also, or only on the daggers?
Only on the dagger boards.
Cant,
And then,
up and down.
yeah, and then tow was not allowed. I'm not dynamically changing tow
On the dagger.
on the dagger boards. So you would have to change fittings, which a lot of teams did, and you could adjust tow.
Between races.
Yeah. And it's similar to a race car, like you would adjust tow to get certain turn-in effects or, you know, handling effects. So that's when we would adjust it. So.
Since there was a force of Dagger Board, was there any teams doing sort of energy scavenging on?
Oh, I don't know. It's a good question, though. We didn't look into it, but I'm not sure on the other teams. The primary thing we focused on was try and keep it steady as possible in the one plane and not use any hydraulic fluid. So that's where blocking mechanisms and all these other control systems came in.
I think we should wrap it up.
Okay.
Thank you.
Yeah, no problem. Thanks.